So, good morning everyone. Change of topic, again I have to admit. And today it may be a little bit difficult in parts, so I hope to walk you through this topic slowly enough that you can get the main ideas of what is happening here in this migration process. Planet-disk interaction. So there are a certain number of points. You see it's very simple today. Type 1, type 2, type 1, type 2, type 3. Okay, I will come back to this, what it means. The problems in planet formation, as we have outlined it in the last lectures, are the following if you compare it to the sample of extrasolar planets. Basically, we had the hot Jupiters. They're very massive planets in the vicinity of the star, and it's very difficult to make them in situ. We have seen Jupiters are most likely made of a solid core, so we have to accrete lots of material, solid material in the first place, and there is just not enough solid material there in the center of the disk. That's for one. And secondly, these inner parts of the disk are very hot, and you cannot typically condense the solid materials in the inner part because they are just evaporating and would not be able to form a core. So, and then you have difficulties to form very massive planets because we have this gap formation there. If you want to form a planet of 10 Jupiter masses and you form a gap when you have reached 1 Jupiter mass, this is of course difficult to grow further, but we have seen yesterday that growth might in fact continue if you look at the streamers there. You might even accrete more later on. Okay, and then we have eccentric and inclined orbits, and we have seen that planets form in a flat disk, and it's very unlikely that you get these eccentric and inclined orbits during the regular formation scenario of planets. So all what I've said in the last days lead to systems, and I will come back to this here today also, lead to systems which are flat, basically, all the planets in one plane. And we know from the observations, this is topic of the lecture tomorrow, that they are strongly inclined and very eccentric. So, but planets are embedded in disks. They grow and evolve together simultaneously with the disk. So we need to look at this planet-disk interaction process. And for that, we look at the later phases of planet formation and consider that the planets have formed, or the protoplanetary embryos, let's say 10 Earth masses or something, see how they evolve together with the disk. In particular, we are interested here how this interaction of this protoplanet, of the planetary core, with the disk changes the orbital elements of the planet. And in particular, of course, as you may know, migration is the most crucial point here. So we have, if you look in these interactions, we have two main contributions. On the left, we have here the spiral arm contribution. And I show you a little animation by Frédéric Massé. And on his homepage, you find several of very nice animations here. So we enter a planet in an otherwise homogeneous disk, and just by pure interaction of this planet with the disk, you generate sound waves. It's just like a boat traveling over a lake. You see the sound waves emanating from the boat, and they have a certain angle with the boat if it goes through the lake. And so these are basically the superposition of sound waves, which give you these spiral arms. Okay, so positive superposition of sound waves, and they are sheared out because of this differential shear in this disk. So we have an inner spiral arm, and we have an outer spiral arm. Okay, this is the typical outcome if you embed a planet in a disk. So what does this have to do with migration? These spiral arms, they are density maxima. You see, they have higher density here, and so these exert a gravitational force on the planet. Okay, and this gravitational force can be translated into a torque acting on a planet, and a torque changes the angular momentum of the planet, and a change in angular momentum means it changes the semi-major axis of the planet, which means migration. Okay. So these overdense spiral arms create torques acting on the planet, which move the planet in the disk. This, of course, only happens if one arm pulls stronger than the other one. Okay? If both arms pull with the same strength, there would be no motion of the planet. Okay? But this is very unlikely. The most likely outcome is that one spiral arm is a little bit stronger than the other, and so you have a systematic motion of the planet through the disk. Okay? The second contribution is the horseshoe contribution here. We know from the motion of particles in the restricted three-body problem, I talked about this yesterday a little bit also. So here's the star in the middle. Here's the planet, or the growing planet we are talking about. These are particles that move near the same orbital distance like the planet here, and they move, if you don't have any other forces, they move on so-called horseshoe orbits. Okay? I will depict this. Animation Frederic Marseille again. Okay? So this is the motion of a particle, and you could just imagine here the Earth, Sun, so this would be a near-Earth asteroid, okay? Which are very common. So as you can see, if they are very close, have nearly the same semi-major axis as the Earth, they come periodically very close to this planet here, and then they get a little kick. They jump from an orbit inside to an orbit outside of the planet. And this can only happen if you exchange angular momentum. Okay, so there will be, every time this particle approaches the planet, there will be a kick and a change in angular momentum. Okay, so when it comes from the outside inside, it loses angular momentum, and here it gains angular momentum. If you have no other forces, no gas, no pressure effects, these will be all symmetric. Okay, yeah, here you gain, here you lose, and so the net outcome will be no change in angular momentum. Both particles will just stay there and not move. Okay, but if you can make it such that these two jumps are asymmetric, then you can have a net change in angular momentum for the planet in the long run. Okay, that's the idea. You make these two jumps asymmetric consistently, and then you can change the orbit of the planet. And this is the co-rotation talk. Okay? It only comes about if you have asymmetric jumps next to the planet. So this is the basics. So you have two contributions. Now we go and see how we calculate this. This I will drop now, so don't read this. So how do you calculate this effect of the disk onto the planet? There are basically two approaches that have been done. First is the linearization procedure, which Phil the other day explained briefly to you. You take the hydrodynamic equations, you have a basic equilibrium state, which is the Keplerian disk. You add a small perturbation, which is in this case the planet potential. The planet is small, so if you add a planet to the disk, it creates small disturbances. You can expand these disturbances in a Fourier series. You can do a modal analysis and can calculate the outcome of this interaction in a linear analysis. Okay, and this has been done in the 80s by Tremaine and Goldreich. They are a very famous paper from 1980, 1981, and 1979. In fact, Goldreich and Tremaine looking at the satellite disk interaction for the small moons embedded in Saturn's rings. Okay, so it's an old topic, yes, and has been analyzed in those papers very extensively already. And then you can calculate the change in the orbital elements, for example, of the embedded moon for the Saturn system, or here for the embedded planet for the protostellar disk. So this is all fine. I will not go into details here. It would be a little bit too much, I think, would cover the next 2 hours, I think, or 2 lectures of mine. So I will basically give you some main results. And then you have a nonlinear possibility. You just do numerical simulations, 2-dimensional or 3-dimensional, and then you can calculate directly all the forces acting onto the planet and calculate the migration speed. So this is more or less also straightforward once you have the codes available. But there are now nice codes, for example, the Fargo code written by Frédéric Massé, in fact, which everybody can download and just fit in a few parameters there, and then you run it, and you have nice migration scenarios there. So everybody can do this now as well. And for this, you have to read the appropriate papers. So what is the outcome of these two approaches here? One first. If you have calculated the torques, which I call gamma in the following, you need to calculate the change in the migration of the planet. Okay? So here is the angular momentum of the planet, mass of the planet, radius, and it means distance from the star, and the angular velocity taken at the location of the planet, which is this expression. If you plug in for u phi here, then if you calculate the torques, and if I say torques here without explicitly mentioning it, I always mean the z component here. Okay, with a flat disk, yes, and as you know, the torques have only one component. The angular momentum has only one component, the z component, and the orbital motion is perpendicular to this constant angular momentum here, and the torques, of course, are always also the z component of the torques. Okay, this is implicitly assumed. So you change the angular momentum by applying a torque gamma on the P. Gamma is calculated by adding all the local torques here, R cross F. F is the force acting on the planet, by the spiral arms, for example. You have to create a gravitational force. So F would be the gravitational force, basically, of an element of the disk with the planet. We integrate this over the whole disk here, surface integral here. You can write here the gradient of phi, the planet potential here. And if you only consider the z component of this R cross nabla phi, you just get d psi over d phi. Okay. That's it. Yeah, that's what you get here. And then you can calculate the migration timescale is just the rate of change of the distance, the semi-major axis of the planet with time. So this here is 1 over tau m, which is the classic migration timescale. And this is gamma, the torques, over the angular momentum of the planet. Okay, so the crucial point is the torques. You need to calculate these torques here. This expression here, basically, either through a linear analysis, where you decompose the potential for the planet in lots of modes, or by nonlinear numerical simulations. Okay, now I come to the different regimes. So type 1, type 2, type 3 denote different regimes of migration. And these are classic notations. They may not be the best choice that people could have made, but this is, let's say, history now. Yeah, everybody uses them, so I use them also. So whenever you hear something about type 1, type 2, you know immediately, aha, I remember this was that type of migration here. Okay, and we start, as obvious, with type 1. So if you add up now the contributions of the spiral arms here, yes, the torque, this is now the torque density. You see the total torque is given by an integral over the radius here, and the gamma over the m is the torque, so-called torque density, is a function of radius. And you can see here is the planet. So you have here the action of the inner spiral arm, and this is the action of the outer spiral arm. So the outer spiral arm pulls the planet back, is always lagging behind the planet, and leads to a negative torque. The spiral arm, which is inside of the planet, on the left side, is heading the planet, and it's creating a positive torque. So the inner disk creates positive torque. The inner disk wants to move the planet out. The outer disk generates a negative torque, which wants to move the planet inwards. Okay? And the balance of this, you have to take the integral over this curve here, and you can see this one is a little bit bigger than this one. The area here, it's bigger than this one, and so the planet is moving inwards. Okay? And these curves refer to the so-called Lindblad torque, and Lindblad is another term which comes from galactic dynamics, is basically the torque created by the spiral arms. Okay? Spiral arms equal, in our context, Lindblad torques, and Lindblad equals spiral arms. Okay? And type 1 means small planet masses. type 1 small planet masses. They do not open a gap. Non-gap opening planets, the migration that those planets experience, we call type 1 migration. Okay. So, and if you add all this up, you come with nice formula, and this is very busy. The basic formula you have to look at is this here. This is the total torque acting on the planet. It's minus, and then this contribution here, times a normalization torque, which is given here. So I don't want to go into details here. There's a normalization, gamma 0 here, and these are contributions of a gradient in the surface density sigma and a gradient in the temperature distribution T of R. And as you can see, this is R to the minus beta sigma, R to the minus beta T, and so these are all positive contributions here. So the total torque, you see the front minus sign is always for reasonably, let's say, stratified disks, it's always negative. Okay. And this is the torque here you can get from linear analysis, Tanaka et al., more than 10 years ago, 3D analytical, that means 3D linear analysis, or numerical simulations, for example. This has been summarized recently by Gennaro D'Angelo and Steve Lubo, 2010, and they arrived at this formula. This formula is actually from that paper here, but they give very similar coefficients here. The question is always, how different are these coefficients in these numerical simulations? So these are basically came out of numerical simulations, very high resolution of Gennaro. Okay. And then we have calculated the total torque. We then can calculate the migration. And as I said before, it's given by the torque basically. So negative torque means inward migration. Positive torque means outward migration. So this negative sign is here. These are inward. And if you calculate the time scales, if you plug in some parameters for this gamma naught here, yes, you can calculate it yourself. You just plug in typical parameters you have from what Phil told you or Leonardo told you here. So you can plug this in and you find type 1 migration is fast. Too fast, usually, to be consistent with the observations. If this had happened for all the planets would be hot. We know there are many hot planets, yes, so there's some truth in it here, but people thought, okay, this is way too fast. We would not have survived even in Jupiter and the solar system. They would have all migrated inwards here. Too fast. I will talk about this later on today. Okay, so the question has been in the last years how to avoid this seemingly rapid inward migration of these particles. And there's one thing one has to notice here, which is pointed out in red. These results are for so-called locally isothermal disks. That means you assume a given temperature profile in the disk, which is typically such that H over R, this quantity, is a constant throughout the disk, and we typically use here 0.05. H over R is 0.05. Okay. Good. And there's one interesting thing here. It depends inversely on the thickness of the disk here, you can see. So that means the colder the disk is, the faster the migration is. Okay. There's basically a simple, I think, reason for this, because the spiral arms that are created, they depend on the temperature in the disk. You see, if you have a low temperature, they're very tightly wound. If you have large temperature, they're very wide spirals. Okay, so if you lower the temperature, the spirals are very tightly wound, and they are closer to the planet and exert a stronger torque. Okay, so this comes about just from the temperature in the disk. Okay, so how can we change this negative inward migration? And the crucial topic here is called torque saturation, which is a difficult topic, and here I hope I do not lose all of you. So, torque saturation, what is this? If we look at the torque evolution with time, so this is the total torque gamma exerted by the planet on the disk, by the disk on the planet with time, and then here you insert the planet at time 0, as I've shown in the movie by Frédéric Macé. You take a small mass planet in an inviscid disk, okay? And there are two types of simulations, isothermal and adiabatic simulations. So both initially, the isothermal is always negative, but the adiabatic simulation here has some positive contributions here, but then eventually later on, they oscillate and settle to a constant negative value, which is equivalent to the Lindblad torques by the spiral arms. Okay? So in the long run, there is no co-rotation torque. These outliers here, they are caused by the co-rotation contribution. Okay? So co-rotation torques, I will come to that in a moment, typically lead to positive torques, while the spiral arms typically lead to negative torques. So initially you have the contribution of the co-rotation torque. It's clear. You plug this planet in, and immediately this horseshoe motion begins. Okay, so planets in the vicinity, so particles in the vicinity of the planet tend to move, pass by the planet, and exchange their angular momentum with the planet, which gives rise to a strong co-rotation torque in the very initial phases. And you can see here, this co-rotation torque can reverse, in fact, the motion of the planet, can make it positive, can move the planet outward. But then, in an inviscid disk, coming back, in an inviscid disk, everything settles out. The co-rotation torques apparently disappear with time. And this is called saturation. The disappearance of the co-rotation torque is called torque saturation. And then we are left in a situation where you have only the Lindblad torques. They were negative because the outer spiral pulls more. And so we have no co-rotation torque, inward motion of the planet. So the question that arises then, how could we possibly maintain these co-rotation torques and ensure a slowing down of migration or even outward motion of the planets? Okay? This is the question that has been tackled within the last 5 years or so. Okay? So how can we change this? And the crucial point is this inviscidness. This is for one. And the second point, which is important here, is the isothermal assumption also. So how to prevent this co-rotation torque saturation? So the co-rotation torque, this is a crucial piece of information here given in red on the slide here. The co-rotation torque depends on the radial gradients of the entropy, S, and vorticity, tilde omega here. So the vorticity is defined as the Z component of the vorticity. Vorticity is the rotation of the fluid velocity, and here we are only interested always in the Z component of it. So we have and the rotation, vorticity divided by the surface density. That is quite often called vorticity. Okay, and then for inviscid and barotropic flows, this is the important point. If you take this and you look at the hydrodynamics of those. Barotropic means the pressure is only a function of the density, P of rho, and then you can show that the time for disks, that the time derivative of this quantity of the vorticity is 0, and the total time derivative of the entropy is 0. This is in general true, of course. This is a quantity which only for disk physics basically applies, for two-dimensional flows, after all. Okay, these equations mean, after all, that these quantities are constant along streamlines. So if one particle has some entropy and it moves along streamlines, let's say along the horseshoe orbit, it will always keep its entropy if there's nothing preventing from changing it by some way. Okay, this is what these equations mean. So the particles take their entropy and their vorticity. So that also means for the horseshoe region, because the horseshoe region is a region where particles mix. You see, you have particles from the inner part coming, particles from the outer part of the disk coming into the same horseshoe region, and they have different entropy and different vorticity, and they mix in the horseshoe region. Okay, so the horseshoe region is a region of mixture of material with different values of S and omega. Okay, and this mixture leads to a wiping out of the gradients there. Okay, the initial gradients in S and omega, if they were there, are wiped out in the co-rotation region, and since the co-rotation torque is proportional to these gradients, the co-rotation torque will vanish in time. Okay, that's the reason. It's called also sometimes phase mixing. And this is illustrated by some plots on the next slide here. So here we have Frederick Marseille, these two here. So we have two particles in this horseshoe region, And here the planet is here, so this is the planet here, and this is the horseshoe region, this is azimuth and radius here. So particles moving at different, let's say, distances from the planets here, they have different velocities here. And here you see the torque evolution for the red and blue particle here, so they are like this, and they are like this here. And eventually, if you calculate the total torque, I have shown you this figure, total torque positive initially, and then settles down here. So the mixing of this material inside of the horseshoe region leads to a flattening of the gradients, as I've said, to a so-called phase mixing and eventually to a zero torque. So the question is then how to maintain these gradients. If we could maintain the gradients of entropy and in particular of intensity, we could maintain possibly a positive torque and slow down the migration considerably. Okay? So, and this is done by adding some disk physics here, okay? Initially, these calculations were done with a locally isothermal equation of state. Okay, this is not quite barotropic, but sort of semi-barotropic. Let's say for a disk which has a globally constant temperature, this would be isotropic then, barotropic. Okay, so, and then you add an equation of state here, for example, temperature evolution here, energy evolution here, and you can take different terms into account. So we have done some simulations here where we plot the torque here. Zero means zero torque. Positive torque means outward migration. Negative torque means inward migration. So if you do, as before, purely isothermal runs or purely adiabatic runs, you have seen these curves basically, it's all negative. But then if we add the radiative contributions one by one, so the blue one has only these terms added, and this one is this one in addition here, so we can maintain positive torques. We can maintain in the long run for its constant base. It settles to a constant positive torque over many, many orbits. This means the planet would move outwards. There's outward migration, so we have completely stopped the inward migration of this planet. Okay, so I have much more time, I think. Yeah? So because the predecessor continued endlessly, so I can just go on, yeah, and you don't mind, I guess. So, okay, so we can see if you add effects like energy transport, and this is clear. This here, this cooling of the disk and the radiative diffusion, they, of course, destroy the constancy of entropy for the particles that they move. You see, if the particle moves now, and the particle cools while it moves, it changes naturally its entropy. So the S over the T is not constant anymore. So the particle can change its entropy while moving through the disk. Okay, and this makes all of the difference. Yes. So then we can see the viscosity. The role of the viscosity. So this is also a viscous disk, alpha disk. We know what alpha is. The viscosity here, 2D radiative model in equilibrium. So you wait until all these torques are settled. And now you look at the torque, total torque, versus the viscosity. And you can see for very small viscosities, nearly inviscid, the total torque is negative. Then we increase the viscosity, and the viscosity, basically, what does it change? The viscosity changes this vorticity gradient, basically. It acts on the velocities, so it will act on the rotation, the vorticity on nabla cross u, and allows then that this vorticity gradient better, is maintained. And you can see you need a certain viscosity here, which is alpha a few times 10⁻3, and then it's positive here. And then for very large viscosities, of course, the flow is entirely disturbed, and then you get a little fall off here again. So this means the viscosity is essential to keep the positive, let's say, or the co-rotation torque operating. Okay, and this is also clear. The viscosity is the only means that the flow, the material which is inside of this horseshoe region, can communicate to the outer world. You see, only if this particle experiences some friction with the outer or inner disk can it feel, let's say, or can some angular momentum be transferred from the horseshoe region to the outer or inner disk. So this is essential here. Otherwise, the horseshoe region, because the orbits were closed, that means the total angular momentum of the horseshoe would never change. if there would not be any interaction. This is what it means. It has a finite amount of angular momentum. Okay, good. That's the role of viscosity. You need it definitely, and you can see or can think immediately that this whole process operates only for planets in a certain mass range. Because if the planetary mass becomes too big and you diminish the mass at the location of the planet, you create a gap or something, it's very clear that then all these effects will reduce, okay? And you will come back to the regular migration generated by the spiral arms, you see? The co-rotation torque only operate in this horseshoe region, and if you empty it out by gap formation, for example, the co-rotation torques will no longer operate, and you have only Lindblad torques left over. And this leads, of course, to a maximum mass above which you follow basically here again these lines here of the standard Lindblad torques here. Okay, and I think this is a good point to stop here and give you the 5 minutes discussion round and then talk later.
She was in Tübingen before, and she left in fact prematurely. After 1 year instead of 2 years. So she was, I think she was getting a contract, I don't know whether she talked or whatever, from or something like this, and he apparently made it better for her. So she left. She had a 2-year contract, but she left. And so, unfortunately, she was good. She was good. It was nice to meet her.
And I know that in computer science, there used to be more parity, and then I think it was when sort of personal computers came on the scene, again, it's gone down. And so it's unfortunate that that's the case. Yeah.
Follow my duties. So, any questions?
Okay, so let's go on. Type 1 we have now understood. Type 1 for small planets that do not open gaps. Okay, and the question of whether a planet opens a gap or not depends, of course, on the disk properties as I have outlined yesterday. And so if the planet increases in mass, we come then to type 2 migration. Okay. Here is a plot of the surface density of a planet embedded in a disk. So here's the radial coordinates. This is the location of the planet. Here's the azimuthally averaged surface density here. And here's the mass of the planet in units of Jupiter masses. So 0.01 Jupiter mass is the black line. You don't see really anything. Then you add some mass here, and then you add more mass, and you can see the density around, let's say, 0.3 to 1 Jupiter masses. You see a clear gap in the disk. And the question is, what you define a gap is, let's say, the ratio of the undisturbed density to this density or so on. You could say if this is larger than a certain fraction, then you call, okay, this is now a gap. Let's say if this is 0.5 or something like this. So this has opened up a gap, and this would not be a gap yet. This is, so whatever. So it's a continuous process. You know, it's clear it varies continuously with the mass of the planet. The point is the gap depends on certain parameters, as I pointed out yesterday, primarily the mass m, which is depicted here. Then it depends on the viscosity. And on the temperature, I show you, let's say, one movie here. The gap depth is dependent on viscosity. This has been done, this movie, by my student Christoph, who's working on planet migration. So here we can see the gap created by the planet in a logarithmic scale. And here we see the same in a linear scale. Okay, these are the same two plots, so just that the eye is adjusting to log scales. I have plotted on the left the log scale, and here the linear scale here. This is radius again. This is the surface density sigma here. Okay, and this is here the value of the viscosity in units of 10 to the minus 3. Okay, so you can see you go on here. So the gap, the higher the viscosity is, the shallower the gap is, because the viscosity, as honey does, it flows slowly into the gap, slowly but consistently. Okay, there's lots of friction here. So very low viscosity, very deep gaps here, yes, and higher viscosity, very shallow gaps. So in the linear plot here, that's why we have done this log plot. You don't see so much in the linear plot. You see some things more in the log plot here. Okay, good. So it's basically the depth of the gap that is changing, not so much the width apparently here. Okay, but it's also clear for very low viscosity, you need to calculate endlessly long on viscous timescales to get the equilibrium solution. This is another problem in these numerical simulations, of course. For an inviscid simulation to get an equilibrium, you may need to calculate arbitrary long timescales, of course. Good, because the gap opening, the viscous gap opening occurs on the viscous timescale, which is the longer, the higher the viscosity is. Okay, so this gap opening means the following. The torques are reduced because you just have no mass there anymore, so that could operate and create the torques. The migration slows, and you have a transition from type 1, low mass planet, to type 2, massive planets, or, put it the other way, linear torques here, non-linear torques here. So type 2 migration can basically only be studied consistently if you do numerical simulations. Okay. Good, that's it. And the gap depends on viscosity and temperature here. I have shown you two gap opening criteria yesterday. I will just go through them and give you the combined criterion by a paper by Orion Krida and others, which combine this gap opening criterion. If this quantity, somewhat p, is smaller than 1, you open up a gap. And if this is not smaller than 1, you have no gap. This is a qualitative criterion based on two-dimensional numerical simulations of a planet embedded in a disk. Okay, so what will happen then? The planet has opened up a gap. What does it mean to the migration rate? This is the most important question to ask, because the torques are not operating anymore. So what determines now the motion of the planet? And the classic point of view is the following, given in red here. In type 2 regime, the planet remains in the middle of the gap, which moves with the disk. Okay? So this is the whole idea. The planet is always in the middle of the gap, where there's low density and it experiences very little or no torques. but to move it must experience some torques nevertheless. But this is the assumption. And the gap, with what speed does the gap move? The gap moves with the viscous speed of the disk. So the classic assumption is that the planet moves here with the viscous speed of the disk. And then just equilibrate. Migration timescale of type 2 migration equals tau visc, which is given by this expression. Phil might have mentioned or not, Rp squared over viscosity. So you have this relationship here. Okay. And this is the standard assumption for type 2. The question is, how valid is this? And this can only be answered basically if you do numerical simulations. And there has been some attempts recently to analyze this in more detail. And also we have worked on this, and as Phil said, I just present now the own work instead of other work and can show you what we have found here. Okay, so these are simulations done by my student Christoph in the last year, basically 2-dimensional hydrodynamic simulations with a net mass flow through the disk. So you add some given m dot that flows through the disk consistently, and then you add a planet in this disk. So this assumes you have a disk that is migrating at a certain rate and has a viscous inflow speed. That's what we wanted to see. So it flows in with the viscous speed, basically the material in this disk. So what happens if you put in a planet now into such a disk? Okay. So and this is plotted here. We put in a planet and have the planet move with the disk. Okay, and this plot does not, or maybe doesn't make any sense to you now. What is plotted here? So here are the changes in the migration speed, a dot planet, over the viscous speed, UR visc. Okay, so one would mean the planet would move always with the viscous velocity. Okay, positive values mean it moves faster than the disk moves. Yeah, or let's say larger than 1, faster than the disk, lower than 1, slower than the disk. It's always inward, okay, but sometimes faster or slower. And these are tracks here for different m dots in the disk. And different m dots, we translate it into different surface densities, because if you have a higher m dot, the surface density is higher. So we just don't quote m dot here, but we just quote the local surface density here. So you can see, and these black dots here is the migration rate after it has moved from r equals 1 to r equals 0.7. Okay, that's this dots here. The diagram is a little bit complicated, but I think you can get the gist of it. Okay, so what it means basically is that the migration rate of the planet is not occurring with the viscous speed at all. There's no clear correlation with the viscous speed. For very low m dots, for very low disk masses, it moves slower. For higher m dots, it moves faster. I mean, this result has basically been seen in numerical simulations some 10, 15 years ago already. Yeah, but nobody really cared so much about it. If one had looked at it carefully, one would have noticed, there is no real type 2 migration. And this is important for the next topic to be touched later on today, for the population synthesis models, for example, because they use type 2 migration regimes to calculate the speed of inwardly migrating massive planets. Okay? And this is a curve, I should have given the reference here, by Paul Duffel and others, also from last year here, obtained by a different method. So also in rough agreement here, yes, for larger disk masses or larger m dots, you have a faster migration here, and for lower you have lower here. And the details, of course, will depend on the disk physics here. Okay, and these are basically the migration tracks here, and this is migrating from out. So there's some initial transient always. You release the planet, and initially it sets up to a new equilibrium, but then it follows basically one single curve here, this new equilibrium here. And here it's at 0.7, and in here it would be at 0.4 or something. So this is an inward motion. Each track is the motion of the planet for a different m dot value. Okay, and that's the idea. So you get a global curve for all different types of m dots for all different types of sigma here. Okay, so this is the outcome. Basically, the type 2 migration that is not linked directly to the viscous speed. It's of the order of the viscous speed. As you can see, a factor 2 below, factor 2 or 5 higher even, a factor 2 below. So, but it's not really directly the same. Okay, is there evidence for gap formation? And there's a clear case, of course, in our own solar system. Yes, here this is the a moon S2005 S1. I think it has a name maybe by now here. Discovered in 2005 in the so-called Keeler gap, which was known a long time ago. There was a little gap in the ring system of Saturn there, and these gaps are created by several mechanisms. One would be a resonant with an outside moon. There are some gaps like that. The Cassini division is of that type. Or this type, the gap is created by a small embedded moon in the middle of this gap. And this is, you can see here, this is the moon. There's the outer disk, inner disk. You can see this is a particle passing by here, and then you can see it passes by this moonlet here, and then it gets some oscillations afterwards, but it continues its motion here around Saturn, which would be way down here. And this is outside here. Outside particle comes from here, moves with the moon, and then it's creating here. And these wiggles here basically are a sign that you can move, let's say, transfer angular momentum from the moon to the outer disk or from the moon to the inner disk. And this was exactly the situation that Goldreich and Tremaine had in their minds when they studied planet-disk interaction in the 1980s. Okay? What happens if you put in a satellite into a disk system here? And it's clear you have opened a gap, and then you could ask, okay, how? Well, this moon must migrate, and so on. This is then another question. What about the migration here? And it's clear this is not a gas disk here. This is a particle disk, but nevertheless, this is a system of collisional particles. They interact gravitationally with each other, so they can communicate. The change in momentum or angular momentum these particles experience here in the vicinity of this moon, they can transmit through collisions to the outer disk here, so we can have some transport of angular momentum there. But it's basically a disk with a sort of very low viscosity, very clean gap. I said here, no pressure. These are particles here, and very little viscosity. So you have an extremely clean gap here. Okay. So I just need to, in the few minutes I have, in the 15 minutes I have, I think, yes. Okay, in the 15 minutes, no problem. Just to check whether you were attending the lecture or not. So no. Okay. Type 3 migration, since this was on my list, this is the very last minute basically. Type 3 migration, what is this? We need this if we want to understand the Nice model and the extension of it, the Grand Tech model. We need to know what type 3 migration is. So all these are important. Yes, type 1 migration is very important for population synthesis, as is type 2 migration to produce hot Jupiters, for example, and type 3 migration, solar system dynamics. Okay. So type 3 migration. I need to show some movies here from Frédéric Macé. Frédéric is excellent in this respect, so I can only divert you to his movies there. Great. Okay. Here we have the motion of a particle. This is now the planet here. And this is the phi direction, azimuth, radial direction. So this is a particle, remember the image of the Saturn's rings, that is inside of the moon and just orbits here the star or the planet Saturn, okay? And if it's outside of the horseshoe region, these lines denote the horseshoe region, nothing much happens, it can orbit there for a long time, okay? Unless you have viscosity or other stuff, okay? This is for a stationary planet, doesn't move radially inwards. Now we change the picture. We change the picture here and have the planet move in radially, okay? This is plotted here, so the planet here migrates inward by some whatever type 1 migration or so on. It hits an inner disk particle here, okay? And this particle wants to go into the horseshoe region of the planet, but the planet is migrating so fast that the particle has not time to be captured in the horseshoe region, but is basically thrown from the inner disk to the outer disk, okay? That's the process of a planet that happens with a particle if the planet migrates sufficiently fast. Okay, then it's not captured in the horseshoe region where it could sit for some time, but it's immediately going from the inner disk to the outer disk. Okay, and what does this mean, basically? This means that to get a particle from the inner disk where it has low angular momentum to the outer disk, it needs to gain angular momentum, because as we have seen, the angular momentum in the disk is increasing with the square root of the radius, so the particle needs to gain angular momentum when it is transferred from the inside out. Okay? And this gain in angular momentum the particle experiences is a loss in angular momentum of the planet. This means the planet will move even faster. this is a runaway process. Okay? So when the conditions are right, I cannot go into the details when these conditions are really right, but under some disk masses and so on, you need to have enough disk mass here that you can move the planet rapidly enough here. Under some conditions, you can create a runaway process that the planet, while moving through the disk, accelerates even. Okay? This is, of course, very strange. And the migration speeds that can be reached, you can imagine, they can be very fast. Okay? You can go within 10 years from Jupiter radius basically inside, if you want. Okay, very fast. Maybe 10, maybe 100 years. Okay, whatever. This is a runaway, and this has been analyzed by Frederick Massey and John Papaloizou and Pavel Artimovic and others then later on, and this is called type 3 migration. So type 3 migration is a rapid migration of the planet which can be either inward or outward. Okay, the setup was just here in the case that we had the planet moving inwards here, but you could imagine initially that it had some outward speed, and then you could have an outwardly moving planet accelerating. Okay, this would be the other way around. Just it seems that it depends a little bit on the initial setup here, but both situations can in fact occur: outward migration or inward migration, and we will see that in the grand tax scenario of the solar system, you need somewhat an outward migration of the planets. Okay, and this is a result of type 3. Okay, I will not go. I think my time is up now. I will not go into more details here, but leave the rest for questions from you. Okay. Yes, type 3 migration depends on the mass of the planet, which is depicted here in the last figure I didn't show. So very good, your question, which was, does type 3 depend on the mass of the planet? Yes, it does depend on the mass of the planet. So this here is the disk mass in comparison to the primary mass here. So these are higher disk masses here, and these are lower disk masses here, and this is the planet mass here. So you can see the most favorable planet mass where this can operate is between 10 to the minus 4 and 10 to the minus 3 Jupiter masses here. And you can see here the regime of runaway migration. Type 3 is sometimes called runaway migration, by the way, in this plot here. And so you can see this would be up here. So for more massive disks here. And it's given here. So for Jupiter to migrate, for example, Saturn, you wouldn't need a nebula which is, let's say, a 10 AU, for example. You could, at larger radii, you would have the right conditions. Yeah, so this plot shows, this is a paper by Frederick and John Papaloizou, by the way. And then you can look it up in more detail there. But this is basically summarizing their conditions. So inside, for small planet masses, type 1, transition region 1 and 2, and then you have, or for higher ones, you have type 3 here, or you have type 2 for large masses here. Yeah. Stefan. So the question is where are the isothermal models active and where are the adiabatic models active? Yeah, this is a very good point. I mean, in principle, the disk, protoplanetary disk, is not an isothermal entity, okay? But what you could say maybe is if you have a passive disk, I think Phil alluded to this a little bit, if you have a passive disk, which is a disk which is irradiated by the star, the temperature is determined by stellar irradiation, and such the disk is isothermal basically, because it has always the same temperature. Yeah, so this is more in outer regions of the disk here. If you have an optically thick disk, yes, an optically thick disk, the energy transport is through radiative transfer, basically, through the diffusion. You have an adiabatic situation, yes, so you need a long cooling time scale, basically. If you want to have an isothermal disk, the disk, upon heating, needs to cool rapidly. So you have a spiral arm going through it, basically. The spiral arm will heat up the disk, but if you have an isothermal situation, it cannot heat up, the temperature remains low. If you have a real disk, which is optically thick so that it cannot cool enough, it will remain hot, the spiral arms will remain hot, and you are more adiabatic. Yeah? So for denser disks, you're adiabatic, which is more in the inner parts, and the outer parts, which are just irradiated, get the temperature from the star, they are more isothermal typish. Yeah. There. I mean, the horseshoe orbits that you have, very first picture here, which in its original version comes from Phil, I think, in his book also. So if you look at the restricted three-body problem in celestial mechanics, okay, you have the star, you have a planet like the Earth, and you take an additional massless test particle, an asteroid, for example, okay? Then you calculate the orbits this asteroid might have, and these are the orbits the asteroids can have for energy conservation, angular momentum conservation. You have in this restricted three-body problem, you have one additional conserved quantity, the so-called Jacobi constant, and this determines the possible motions of particles in the system. So this is an exact solution to the three-body problem, which occurs everywhere in the solar system. The Trojan orbit in Jupiter here, asteroid orbits in the Earth, and so on. So this is the solution of the three-body problem. Yeah? Particles which are close here move within this region here. Particles which are outside, this one here, moves in circles. Okay? Particles inside move in circles, but particles here, they can move in this horseshoe region. Three-body problem. Yeah? And the Hill sphere basically the Hill sphere size is basically the width of this horseshoe region. Okay. And we call these orbits in here, we call librating orbits, and these outer orbits and inner orbits we call circulating orbits. Okay. These ones circulate here, or this way, and these ones librate in the horseshoe region. Hope that made it a little bit clearer. Other question? Do you take questions still? Or he was first. No? Do you want to ask a question?
Just a quick one. Where are the angular momentum kicks coming from at the end?
Here, you mean? Oh, because if you have a particle here, directly here on this separation line between this inner and outer region here, the so-called separatrix, by the way. Okay, this particle here approaches the planet, and when it comes from here, it's accelerated by the planet, because here's the gravity, it's accelerated in this direction here, its angular velocity increases, and an increase in angular velocity means it has to move outwards. Okay? You see, it comes here, it's attracted by the planet, so it increases in angular velocity, and increase in angular velocity means higher angular momentum, and so it moves outward. Clock. Conservation of energy and angular momentum. Very simple. It leads to just take a little program and calculate this three-body. It's a three-body system. It's very Newtonian three-body, nothing else. It's the motion of particles in the Newtonian restricted three-body problem. Still very complicated.
So on this one, I think we stop the session.
Okay.